everyone. Welcome back to the last talk of the first day of our conference. So today we've had speaker from Germany, Canada, Spain, and US. Next, we will welcome our next speaker from the Southern Hemisphere. So we'll have Jan de Gier from Melbourne, Australia, to tell us about inhomogeneous q-deformation of the Tsetlin library.
Yeah, thank you, Jean-Ting, and good morning, everyone. It's 7 a.m. Here in Melbourne. I want to talk about some collaboration with these people, Arvind, Sarah, and Anna, and we had a little bit of help of Darich as well, who's here in the audience. So I'm really motivated by stochastic processes based on the Hecke algebra because they're related to special functions. I work in the area of solvable vertex models, and often we are interested in stationary state that we can compute exactly, and they have sort of interesting properties. In particular, there's lots of combinatorial and geometric interpretation of these stationary states, so that connects to this audience. So the plan of my talk is I first want to talk a little bit about Tsetlin library. I'm not entirely sure how familiar people are with this, and then we'll start about the q-deformation of it. So the Tsetlin library is this library of distinct books arranged in order 1 to n, and you shuffle this in the following way: that you pick a book with probability xi, and you put it back on the left or at the front after reading. And you can interpret this as a random to top shuffle Markov chain on permutations with this generator. And you act on permutations from the right, like this. And so what this product of elementary transposition does is it picks the ith book and it puts it back at the front. So the action is that you pick the ith number, and you put it at the front of the permutation, and you do so with some probability x by I. And so you can write down the transition matrix. So here, like maybe look at the first row. It tells you where 3 to 1 can go. It can go to itself with probability x3. It can move to 2, 3, 1 by moving the 2 to the front with probability x2. And can go to 1, 3, 2 by moving this 1 to the front with probability x1. And then, so this is a Markov chain for which the rows all add up to 1. Because we use this condition that all the probabilities add up to 1. And you can now ask what is the right stationary state. And that is given here. And you see in this little example that there's quite a bit of structure there. And you might be able to compute this stationary state. And indeed, this was already done in 72. The general form, these coefficients of your stationary state have this particular form. So that gives you the stationary state, but it gives you more. It gives you the sort of mixing times or strong stationary state. So for example, if you'd like to know the expected time to reach a particular permutation from any starting position under this Markov chain, then you can compute it by this particular formula, which I won't explain in this talk. So you can take a derivative with respect to these xi's. And compute this expectation mixing time or hitting time. And these are bounded by the expectation on the long permutation, and that can be proved to be order n log n. And that will then give you the mixing time n log n. So that's a well-known result. So I want to talk a little bit about how you compute these. You can do this brute force or within the symmetric group language, but there's another way of computing stationary states using this concept of geometric finite semigroups, and I've listed a few names of people involved in that. So how does it work? You take the set of all non-empty subset of 1 to n, so P3 is listed here. And then you consider multiplication in this in the P of n is the union of sets. And so this forms what is called a left regular band, which means it satisfies this this condition here. So u dot v means the union of u and v. And so if I do that and a union again with u or v, then nothing changes. And then there is a theorem. Again, I won't explain that, but if you have such a left regular band structure, there is a very convenient way to compute the stationary state distribution of such a Markov process that has this property. And I'll go through an example so you get a feeling for what's going on. So here's the example of constructing the subsets of 1, 2, 3. So we consider 1, 2, and 3 as generators and start with sort of like an empty set. And you can add 1 to it, or you can add 2 to it, and you can add 3 to it using the generate. So the blue lines indicate the actions. So once you have, say, 1, you can add 1 again, but that doesn't really change. So this is the left regular band property. It doesn't change the set 1, but you can add now 2 or 3. And so if you add 3, you get the set 1, 3. And I'm going to remember the order in which I've added elements. So once I get the set 1, 3, by first adding 1 and then 3, I again have a stabilizer by acting with 1 and 3, and nothing changes, but I can add a 2 to finally reach the full set 1, 3, 2 in the order 1, 3, and 2. And so in this way, you can, of course, there are 6 different ways of getting the full set 1, 2, 3, depending on the 6 different orders that you can add a 1, a 2, and a 3. And now, if you wanted, now you can sort of consider the pre-image of every permutation, because that will be important for computing the stationary state. So I define this pre-image where you take a particular permutation, let's take 1, 3, 2, and you just look at the path that leads you back to the origin. And that's called the pre-image. And these paths all have the form is that if you identify such a path and start from the top, you'll add a particular element. Then once you get to that element, there's a stabilizer. Namely, you can add this element again and again and again, but nothing changes until you add another element by 2. And once you've had that, then you can stabilize by both of them, and so on. So then you can construct a Markov chain on this expanded graph, which is like an infinite Markov chain because you have these infinitely many stabilizers you can have. So you should really think of this as a graph with infinitely many paths on it because of the red loops. Okay, so then the statement is, because of the left regular band property, the stationary distribution of this Markov chain on this expanded Cayley graph is just a product measure of all the axes. So for every time you add an element, you do so with probability x a, the a being the element that you added. And so then the stationary distribution, this is just a product measure. And then the final step to get to the stationary distribution on permutations, you then have to lump. And the lumping occurs in the following way, is that you sum over all pre-images of a particular permutation in that graph of the factorized measure on the extended Markov chain. So to give an example, let's say we want to know the stationary distribution of the Tsetlin library for permutation 1, 3, 2. I have to sum up over all paths in this pre-image. And so there's one blue path, but there are infinitely many red stabilizers. So how do I compute the sum? So the pre-image is in this notation given by adding a 1 from the top, then stabilize with 1, adding a 3, then you can stabilize with 1 and 3, and then finally adding the 2. So again, that's this path here. And so adding a 1, I do so with probability x1. Stabilizing here, I can do infinitely many times, just a geometric series. It's 1 over 1 minus x1. Then I add a 3, with probability x3, stabilize with x1 and x3, and finally adding x2. And if you simplify this using the property that all the probabilities add up to 1, you get this expression here, which you may remember is of the form of the stationary state example that I gave at the beginning. So this way you can compute all the components of a stationary state for arbitrary size. So this is quite a nice construction, and in our work we tried to we did do it, q-deform this process. So now we want to consider the Hecke algebra instead of the symmetric group. So here, just to remind you of the Hecke algebra, so really the only thing that changes is that you deform the quadratic relation by introducing a q parameter here. And then the q analog of a random to top shuffle is really replace the product of elementary transpositions of the symmetric group with these Hecke generators. And you can act with this on permutations. So the action of Hecke on a permutation from the right is equal to q times the transpose permutation if pi I plus 1 is less than pi I. And if pi I plus 1 is larger than pi I, then the action of Hecke will be the transposed permutation plus q minus 1 times the original permutation. So if you divide all this by q, you see that q inverse ti has a probabilistic meaning. Namely, it acts deterministically when pi I plus 1 is less than pi I, and it acts with some probability. It changes with probability q inverse, and it stays the same with probability 1 minus q inverse. Okay, so in this way, with the right normalization, this becomes a random to top shuffle with an additional probability q inverse built in. And you can just you can then also add these variables x, and the way to do it is that you put an operator on the right. So after you've shuffled with each product of ti's, you then look at the permutation that you're getting, and the operator x or chi will give it a weight that I will call y pi I. If this should be y pi 1, by the way, y pi 1. So the permutation that sits at the front. I call this y to distinguish it from the x's, because we will use a normalization that will become clear later on. There will be this overall power of q, and the x's really will become our probabilities. So these y's are like some q normalized probabilities. So an explicit example is this matrix that you see here for the case n equal 3. So it looks very similar to the example that I gave earlier for a symmetric group, but now there are some factors that depend on q in this way, or rather depends on q inverse. But this matrix still has nice eigenvalues, so you can compute those. And in this example, they're nice, but they stay nice for larger n. And also the stationary state still looks reasonably nice. So now there are some q's floating around, but the expressions don't look too complicated. And indeed, there is a way to give an explicit formula for what these elements look like for arbitrary n. And that was sort of the main results of our paper. And I'd like to tell you a little bit now on how to do that using this semi-group construction. So for that, we need to lift union of sets to an action on flags over finite fields. And so just referring here to Ivahorian, Helps, and Ram, the main literature on this. So just to remind you, again, I'm not too familiar with the audience, just with these two slides are probably very basic for most of you. So what we're going to do is form a semigroup formed by union of sets, replacing the union of sets by an axiom of flags over finite fields. So if FQ is the integer mod Q, then G will be the linear group over FQ. And we think of a flag as a sequence of subspaces of FQn, such that every subspace Vi has dimension I, right? And so the set of all flags is the set of all such sequences of subspaces. And there's one distinguished flag, which is the standard flag, which is just the spaces that are spanned by the standard basis. Okay, so just to give you an example, in case n equal 2 and q equal 2, it's very basic, then the number of lines in f and q is a q number, and the number of flags is the q number factorial. And so in the case that n and q are both equal to 2, then 2 number 2 is equal to 3. And you can indeed identify 3 lines. There's the standard basis lines, E1 and E2, and there's one more line, E1 plus E2. Any other, when the coefficients of the lines become 2, then because Q is 2 and we compute mod 2, there's no further lines. There are also 3 flags, and the flags are E1 in E1, E2, then E1 plus E2 in E1, E2, and E2 in E1, E2. And I want to, the reason I'm giving this example is really to introduce this notation here. I want to think of these two belonging together, and they can be written as the first column 1 alpha, where alpha is 0 for the first case, and alpha is 1 for this second case. So when I have E2, alpha is 1, and then I just have E1, I get this. But they belong together in this first column, and the 2 choices of alpha. And then the second case is where the first column is given by E2. So now the first column is 0, 1. And then to complete the space, I add the second column to the full span. And so you can play that game for n equal 3, etc. And you get this list of double coset representatives or equivalence classes, depending on how you want to think about it. So in this case, I would get, say, the span of E1 plus alpha E2 plus beta E3 inside the span of that first vector plus the vector E2 plus gamma E3, etc. And suggestively, the way this is written, I want to associate this to a permutation 1, 2, 3, and so on. So if I would first start with, say, the line E2 plus alpha E3, and then add the line E1 plus beta E3, I would then associate this to the permutation 2, 1, 3, corresponding to the entries. So read by column. The first non-zero entry along a column, I normalize to 1, and that will give me the 2 in row 2, 1 in row 1, and 1 in row 3, and so on. So with flags over F and Q, we can associate permutations in this particular way. Okay, so what then is the action of the random to top generator on flags? So it turns out that this action is by adding lines and variables and removing duplicates. So what does it look like? So if I have a flag, I act on it with this random to top generator in the following way. I take a sum over all possible lines. Remember the NQ lines. I add to every subspace the line Lj. So Lj itself, then V1 plus Lj, etc. Vn minus 1 plus Lj. So this will, so one of the subspaces that gets added a line will become isomorphic there will be a duplicate. So this little head means that you remove the duplicate so that you can get a flag again of subspaces that are all of dimension I. And after you've done that, you associate these variables x to it by this chi of Lj, where chi of Lj is chi of L is xi, if the line that you added started with the ith standard basis vector plus a linear combination of lower basis vectors. So the ith is the sort of the smallest non-zero entry of that, and that will get an xi. So any specific line of this form, ei plus a linear combination of lower standard basis, so this sum runs from I plus 1 to n, we'll get a probability yi, which is xi over q to the n minus I. So in the flag language, these yi's are the probabilities for picking a particular line. And all these lines, each one of these gets the same probability yi, and then this vector of q now is clear because it corresponds to the number of lines that start with ei that you can get. So all these linear combinations, each one of them contributes a vector of q. So another way to see this is that you can, so on these representatives, coset representatives is by inserting a first column. So maybe I run through the example. So let's say I wanted to add the line 110 to the flag 011, sorry, 011 inside 011 102. So what I do, I put this line in the first column, and I write my flag as 011 is the first column, 102 is the second column, and then I complete the space with the third column. And now I bump this added line into it. So my first column will be replaced by 110. What was the first column will be bumped to the second column. And now the second column will be bumped to the third column, but actually the second column, 102, is a linear combination of these first two columns in F3, because we have that 102 is 110 plus 2 times 011 in F33. So we compute mod 3. And so we remove that. So this line doesn't get bumped, but it gets removed. And we just like with the last column. So this is the action of adding lines in this using these coset representatives. And you see that the permutation associated with the flag that I chosen is 2, 1, 3, and it after the action of adding this line, it now becomes 1, 2, 3. So you're changing the permutation, the associated permutation. Okay. So to put it all together, then you have to now think of this expanded KR expanded Cayley graph and identify the pre-images of flags to compute the stationary state of this q-deformed Tsetlin library. And so it's a more complicated picture than for the symmetric group. Just to tell you what's going on here, I start with the empty subset, and I'm now adding lines to this. So the rest in this example, the example is n equal 3, q equal 2. So there are 7 possible lines that I could add. I've just listed a few examples. I could add E1, E1 plus E2, or E1 plus E3, and then there are 4 more lines that I could start with. Once I've done that, I can add E1 again, but that doesn't change my subspace. But I could add like 2 plus 3, or 1 plus 2 plus 3. And if I do that, I will get into two-dimensional space spanned by E1 and E2 plus E3. And once I'm here, there's a stabilizer again. And after this, there are q-square lines to get me to the full space. So there are paths like that. And the same, if you wanted to end up here, you first add a 1, stabilize by 1, then you could add a 3 or a 1 plus 3 to get you to the span of E1, E3, which is stabilized itself by 3, 1, and 1 plus 3. And then there are 4 lines that you could add, 2, 2 plus 3, 1 plus 2, 1 plus 2 plus 3 to get to the full three-dimensional spans. And now if you wanted to compute the stationary state of the q-deformed Tsetlin library, we have to follow the same process by lumping over the pre-image of a particular path. So if we wanted to know the stationary state of psi 132, we just looked at the space 1 corresponding to that permutation, 132. And look at the pre-image. So that's all the parts, including these infinitely many stabilizing parts that go to the top and sum over them. So again, if I'm at the top, I go along the first edge. I do so with probability y1, with which I've picked this line 1. Once I have the subspace E1, I can stabilize with 1, and that will give me this denominator, 1 minus y1. Then I can go from here to there by adding 3 with probability y3, or adding 1 plus 3 with probability y1, because now 1 is the smallest EI, so this line will get probability y1. And there are q minus 1 such lines. So in this example, q is 2, there is only 1 such line. The coefficient of this 3 is 1, but that you can imagine that I could add multiples of 3 there. And then it's stabilized by these lines, and that will give me a factor 1 minus y3 minus q times y1, because there are q lines of the form 1 plus something times 3. And then I go down with each of these 4 lines, and the first 2 come with probability y2, and the last 2 come with probability by 1, because the 1 is the smallest standard basis vector. And so this will give me in total q y2 plus q times q minus 1 y1 if you account for everything correctly. And then simplifying, you get an expression like this, which you can check with my previous example, will give you up to a factor of q squared, exactly the stationary probability in when you act with the Hacker generators on permutations directly. So this is a way of computing those stationary states. And here's a general formula. It's the main theorem. For any n, and there are certain statistics here that you need to know. You can compute the stationary state by computing a formula like this. So don't really want to go into full details here, but you can read it in the paper if you're interested. There's a slightly more combinatorial formula, so this can be simplified a little bit, but this is the one closest to the construction I think I gave. So I'm almost done. The final thing is that you can compute mixing times. So if you remember, we can compute the hitting time, the expectation to reach a certain flag from a given starting position is given by an expression like this. And now we know all the size, so we can compute it. And if you give certain probabilities on picking your flags, so this is a natural way to do it, you get that these mixing times are the same as for the original Tsetlin library, or the n log n, if this p is 1. But you can go faster if q is larger than 1 and you pick p also larger than 1. So adding some randomness mixes the chain faster. So that's it. So what we've done, construction of the stationary state via projectional geometric center group Markov chain. So for the formulas I gave, they were computed using this left regular band on flags, but we don't yet have a proof directly in Hacker, although I think it should be possible. We have the generalization to words where you can have repeated elements. As I said, there's faster relaxation due to the enhanced randomness. And we'd like to apply this to other Markov chains. So, for example, multi-species RCEP or yeah, other things. All right. Thank you for that.
Let's thank Jan de Gier for the great talk. You can see all the reactions. Any questions?
Yeah, I had a question, I guess. In the example, it looked like that you showed, it seems like the number of FQ points of the associated Schubert cell shows up in the denominator there, but I don't know if I'm following the notation. And is that something that always happens in these formulas for the stationary states, or is that just a coincidence? It was just like the Q squared that you had.
Which formula?
I guess the more general formulas that you just showed.
This one here?
Yeah, it just seems like the way the process is defined, the number of FQ points in the Schubert cell should show up somewhere, but I don't know if that's necessarily what is.
Maybe it is. I don't know. I simply don't know the answer to that. Maybe someone else in the audience, but because I'm not an expert on Schubert cells, but that may be interesting observation.
Okay. Yeah. Thanks.
Any other question?
I had one. This bottom to top action on flags that you were describing, is this from your paper, or where's this? Is really very interesting to me. Is there good resources for this?
Yeah, so I think the bottom to top or random to bottom is that all of that is without the x's, without the probabilities, is work of Dick Reiner and Sarah Brown and collaborators. So our main work here is to add the x's to it. Yeah, in a way that preserves nice properties. Yeah.
Right, but I mean, like specifically this action that you were describing, like on the flags themselves, though.
Yeah, that's already Ivahori. The main